Okay. Yes, indeed. Troubleshooting Live YouTube. Hello, everybody. Welcome to TGIK this week. My name is Duffy, and I'll be hosting this episode. Turns out the problem that we had was apparently we were doing some testing with another uh, prospective member of our cast, and that tied up the encoder and didn't allow me to recreate the session. So now we're back. Welcome back to TGIK number 75. In this episode, I'm going to be exploring a number of different ways to kind of troubleshoot and play with CNI implementations. Because I had some work this week that kind of covered that, and I thought that was pretty interesting stuff. So welcome, welcome, welcome. Let's take a look at the chat, see how we're doing here. Give me just a second while I fumble with things and figure out what I'm trying to achieve. On the fly. All right. Okay, so we got Sean Smith signing in. We got hello to Christopher and Darshaname. You were really close to first. Rory, hello again. I hope you're having a great time over there on the other side of the pond. I'm actually going to be in the UK for 3 weeks in June, so I'm looking forward to being over there. We should try and meet up. Hello to Joe and to Jay. Welcome to Forrest. Hello, Forrest. Hey, Peter. Good to see you. I'm glad to see you this episode. I know this is one that was going to interest you. Hey, Christoph from Germany. Hello, Joy and Brian. We have all kinds of wonderful folks joining us for this episode. Lamati is joining us again, and he reminded us that Chris has actually done a number of episodes on CNI as well. And those are broken into our notes. Let me put a link up to the HackMD, unless, George, if you could handle that, that'd be awesome. Just put up a link to that HackMD. My friend Joe Searcy from Atlanta. We've got some people from Sweden. Hello, Federico from Sweden as well. Is the audio sped up? No, I'm just talking fast. And this is, we got Steve from Mountain View. We got Amine from Strasbourg. Abhishek from India. And Martin from the Netherlands. And then we have my friend Sarab, who's part of Team Beast, because he is usually on the East Coast. So, all right. Welcome, everybody. It's good to see y'all. And let's dig into our notes and see what we got today. I'm going to flip to the screen here. All right. So all right, this is our HackMD for the day. And it's got a number of interesting things in it. Let's kind of go through and see what we got here. If you want to keep notes or refer to notes that are being created in here, please feel free to do so. We're going to apparently, I'm probably covering some of the stuff that Chris has covered, but in a slightly different way, in like kind of a troubleshooting, understanding way. So I think Chris is kind of the dyed-in-the-wool hacker. So when she gets her hands on a CNI, she's going to dig down into the nuts and bolts and figure out how it works from the code perspective, which I really admire about her. I'm more the operator. I'm going to kind of approach it from the perspective of what is it actually doing it, and how does it work operationally from my own personal perspective. And I think it kind of takes a village. We all kind of have to approach it from our own perspective here. All right, so our first article is another Vault on Kubernetes write-up, and I think this one's actually pretty good. This was actually put out by Jan Geiger. It's on the IT Next website, and in here he's actually kind of talking about another solution for Kubernetes, or landing Vault agent on Kubernetes to renew things. Let's see, what does he do in here? So in this case, he's using Minikube, and he's bringing up a Kubernetes cluster that way. Actually, he's using kubeadm to install things as well. So I do this with Kind, and we'll talk about a little bit about what that's about here in a little bit and describe it. He's also pulling down Vault, running a Vault server, I think externally to the cluster, configuring the authentication method for Kubernetes. This is actually just enabling Vault to authenticate to Kubernetes. The way this works is kind of being able to do service account lookup with the Kubernetes API. So when you have a service account token within the cluster, you can use that token to authenticate to the Vault API. Then once you actually are authenticated by Vault, it provides you a Vault token, and that Vault token is how you would actually authenticate to the Vault to get your secrets and stuff. So interesting stuff in there. Talks about the RBAC role. We need this auth delegator piece, which is kind of basically how we are able to understand whether the service account itself is valid. And they get into different use cases, different patterns for using Vault within Kubernetes, like the sidecar model. I've seen a couple other ones recently that I thought were interesting. I know that Seth Vargo actually just put out recently an article talking about a model for Vault on Kubernetes as well, which I thought was pretty interesting. So yeah, definitely worth a read. Let me move on to Grafana dashboards for Kubernetes administrators. This is another one of the interesting articles that has come out this week. So most Kubernetes clusters that I touch on a regular basis are leveraging Prometheus for information, and Prometheus ties pretty well into Grafana, so for visualization and things. I think what this represents is a number of, okay, so he's actually leveraging the mix-in stuff that Frederick put together, which is awesome. And this provides you some pretty interesting graphs around the API server, controller manager, and scheduler, and the kubelets themselves, which I think will be pretty useful. They also have some graphs for kube proxy. Don't let me zoom in on them though. So yeah, and leveraging JSONet to build them out. The cube dashboards for these things. I bet you those are actually pretty useful. I think it'd be a pretty interesting TGIK to kind of get into those things, because I suspect what he's showing, I'm not able to, unfortunately, dig in here a little bit. Let's see if that works. Okay, so this is talking about rule sync latency for kube proxy, so how long it takes for the rules to actually get synced up. Describes what the ones that are being held up are, describes the kube API request rate, and how many instances there are. Oh, so this is actually measuring latency for the application of rules for kube proxy across the cluster. This is an interesting graph, especially as you grow a larger cluster, because one of the challenges that we have with kube proxy and IP tables at the moment is, like, as we grow the number of services, or we start introducing a lot of churn within Kubernetes, we actually start seeing the amount of time it takes for IP tables to converge on the entire rule set. It takes a little bit longer. Do I sound a little higher? I've been hitting the caffeine a little bit this morning, so maybe that's what it is. I hope it's not too bad. All right. So yeah, I should actually slow my voice down. I'm talking too fast. I suspect that's actually really what it's about. Mainly because I was a little nervous by the fact that I had to create a new stream. So that's probably what that was. All right. Audio clipping. Well, I guess it's probably the speed thing, I suspect. So I'm going to bring myself down to kind of a regular speed of speaking rather than, speaking like a squirrel. So we'll see if that changes anything. Please keep giving me feedback and let me know how it goes. All right. So that is the kube proxy stuff. And then these other graphs, I get into the API server and the controller manager, and I suspect probably provide some pretty interesting graphs around what you can get from them as well. So it would be really interesting to kind of play with this, I think. But check it out on your own. And, if you're interested in it, maybe put up an issue in the TGIK repo, and we'll see if we can make an episode out of it. The next thing that we're going to talk about is Kubernetes 1.15 Alpha 2 is out, and we're also, with that Alpha 2 release, we're also pushing out a 1.11 release. Let's take a look at the output of that. So this is the 1.15 Alpha 2 release, and then I suspect 1.14. And then here's the changelog for 1.11. Talks about what's happening in the 1.11.10. So this is what's happened since 1.11.9. Looks like we made some changes to Prometheus and some of the other add-on stuff. We increased some of the Azure settings. If you're making use of the cloud integration provider in Azure, this stuff would affect you. Got some changes to GCI. The node problem detector configuration is now coupled with Kubernetes release. That'll be interesting. Node problem detector is a really interesting project, actually, because it enables you to kind of understand the state of your clusters. Liget has restored some of the configuration flags of kubectl, so now you can continue to pass username and password if you're doing that. I've not really run across anybody doing that, but apparently somebody was. The update to cluster autoscaler has been changed, and then this is probably where it's about. Qubit won't evict a static pod with priority system node critical upon resource pressure. So that's probably a driving factor for this release. What that would mean is, if you're leveraging a kubeadm cluster, a static pod might be your API server, your controller manager. And so if you are under pressure, if the qubit itself is receiving a lot of pressure for I/O or memory or CPU, then what ends up happening is there's going to be an eviction. And it looks like from this issue, just from the title of this issue, what's happening is that the qubit was actually evicting pods that were in system node critical, presumably because they were static pods and that wasn't being taken into account or something like that. So without digging into the issue, that's kind of what I would expect from reading that. The next article we have is Deadlines Are Horrible. Let's take a look at that one. I love the title. Deadlines are horrible. I mean, who doesn't love that? So it says, "My dearest SIG release heroes and heroines, can I bend your ears for just a second?" This is Mr. Tim Hawken. So this is actually, this was actually, I think, the result of Tim being very transparent and very awesome as Tim is. And he talks about basically, he's been trying to catch up with a bunch of stuff, and there's a ton of crypts in this round for 1.15. And he feels as though he might have missed a couple. So if you were waiting for Tim to review your CUP and it just didn't get happened, he was like letting you know, hey, I'm sorry about that, but please raise it to me. And it's a little frustrating. So yeah, I mean, I think it's this whole community is built on people like you who are listening today and who are logged into this episode, people who are out there hammering on their keyboards, fixing Kubernetes bugs left and right. it takes all of us, and we are all people. We all make mistakes. We all get overwhelmed. Don't feel like you're alone in that. There's a ton going on all the time. So definitely keep that in mind. None of us are fallible or infallible. The next article is actually talking about WireGuard for Kubernetes. Now, this is an interesting one. And I personally have kind of a lot of opinions on this subject. So let's just talk through that real quick, and then we'll talk about these two projects. There are two projects that I know of that implement this. There's the WireGuard one that's actually getting some press in the community right now, delivered by Gravitational, that's called Gravitational Wormhole. And then there's an older one that somebody used to work with back in CoreOS named Squat that built called Kilo. What this enables is the ability to form effectively an opportunistic encryption mesh between all of the kubelets in your cluster. And what I mean by that is that the way that this all stands up, you would set up effectively a way to ensure that you're encrypting all traffic back and forth between the nodes on a wire. So if you're going to deploy a Kubernetes cluster into an environment that you don't necessarily trust, what you might be concerned about is, how do I make sure that I can encrypt all traffic back and forth between all of the workloads without having to understand things like MTLS and that sort of stuff, and having to build into my application how to solve those things, right? I mean, like most patterns for ingress, for example, may choose to terminate TLS at the ingress controller and then don't encrypt it back down to the pod, which means that that traffic going back and forth between the ingress controller and the pod is unencrypted. So how can we make it so that we're just doing encryption everywhere that we can without having to introduce any more complexity to our solution per se? In this case, the Gravitational Wormhole and the Kilo project, what they're doing is they're basically saying, look, let's just stand up a WireGuard configuration here that your CNI will ride on top of. And in so doing, we'll make it so that when traffic moves back and forth between nodes, as long as it's destined for something that we understand in the routing table, we will opportunistically encrypt that traffic, ensuring that pod-to-pod traffic is always encrypted because node-to-node traffic is encrypted, which is pretty cool. I think that actually one of the major reasons that people end up getting wrapped up in, service mesh or service mesh are around things like Istio and tools like that, are because they feel like the importance of having MTLS back and forth between pods overrides that complexity, right? Or that it introduces. And sometimes maybe that's not true. I think that the complexity of Istio sometimes ends up cooling off people's zest for the project itself. But think about the problems that you're trying to solve. If the problem that you're trying to solve is that you're going through a security audit and you need to be able to ensure the traffic is encrypted on the wire, these are a couple of examples of ways to achieve that without having to adopt a model like Istio and all of the complexity that it brings. So interesting stuff here. Let's see, any comments on that? Yeah, my voice getting a little bit better now that I've calmed down some. How does it do that? Let's see. I think Huawei has put out an awesome post on how they addressed the IP table issues with cilium. Yeah, cilium actually, we're going to dig into it a little bit, but cilium has some interesting ways to solve this problem. Some of the other ways are there are a number of kind of attempts to fix the kube proxy problem. And we'll kind of talk through a couple of those. Like KubeRouter tries to address this, actually does address this. Cilium addresses it in a similar way. We'll kind of play with that kind of stuff. All right. So that is all I wanted to say about WireGuard. Very cool project, very exciting stuff. I'm loving seeing, kind of that encryption on the wire happen as a lower level concern. I don't think that it necessarily belongs as a sidecar, and so I think it's good to see both of these two models being explored. Very cool stuff. The next article up is why script-based deployments on Kubernetes don't scale. I haven't read this one. Let's see what this is about here. How do I deploy my application? They start talking about Spinnaker versus kubectl or customized scaffold. There's a variety of different ways to kind of try and solve configuration as code for Kubernetes. Deploy the manifest stage, sophisticated and complex deployment strategies, multi-cluster deployments. I think they're talking, this is a pro-Spinnaker article. This is an article that's talking about leveraging Spinnaker to manage the continuous deployment aspect of your application, rather than trying to solve this in perhaps a way of like, trying to script this in like another CI environment. And so that's an interesting piece. Definitely worth a read. Some of the other interesting patterns that I've seen in the field recently around this are kind of more toward the GitOps flow. And there's I think a few different ways to think about GitOps flows in general. But as a quick overview, what I've seen recently that I thought was interesting is that people are starting to adopt a model wherein they have some agent running on the cluster that is watching for configuration updates or updates to a particular GitHub repository, maybe on a specific branch. And when that branch updates, it will pull those configurations into the cluster where that agent resides and apply them to the cluster itself. And in this way, if you think about it, it's a little bit more kind of toward the Kubernetes model, in which we have a desired state, which is represented by that GitHub repository and those manifests held within it. And we have our actual state, which is represented by the state of those deployments and mechanisms that would be deployed by the YAML inside of that GitHub repository. And we're just kind of, we're using a reconciliation loop to make sure that when our desired state changes, we can go about making our active state or observed state kind of, come to terms with that. And I like that model. And I think that it's actually significantly more scalable than some of the other models around like push. There are definitely some challenges, like how do you manage things like, canary rollouts, and those sorts of things. And I think that becomes kind of interesting, like when you start thinking about them, or those things become kind of a challenge because you have to start thinking about, what does a canary rollout mean when you're doing a GitOps flow in which you have an agent in every one of 20 clusters, right? If you make a change to the upstream GitHub repository, do you want all 20 of them to apply? Or do you want to break those clusters up into a smaller portion so that you have A, B availability across particular subsets of those clusters? It's an interesting space, and I think that there's a lot to be explored there. I don't know that we have like a straight up answer for how it all works. You see most of your customers using Flux. Flux is actually starting to come up more and more often. I'm starting to see Flux. I've seen a few people working with Argo. I've seen people kind of building their own thing. There have been a couple of different projects out there that have come up and kind of addressed this particular space. But yeah, it's definitely an interesting space. All right. This is a great article on how you can help localize Kubernetes docs. We have people from all over the world in this episode right now. Y'all, I'm looking at you. Right? We have people from the UK, from Germany, from other places, from India in this chat right now. What we're doing is we're kind of calling out to the folks who are in other parts of the world that want to help us localize the documentation for Kubernetes. And if you have some time, feel free to read through this article and see if there's something that you can contribute to. I think it's important to the adoption of the project that people are able to understand these things in their own language. And so if you feel like this is something that you could use to that you could contribute to, please jump in and help us out. It's really great. Obviously, like if you speak another language, or if you're trying to troubleshoot something like Kubernetes and you can't like get any content that relates to you in your language, I can imagine how that would be very frustrating. So I'm sure you can too. All right. Those were all of our articles from this week. Oh, nope, we got a few others. Latecomers. We talked about localize. We talked about Docker Hub maintenance. Oh yes. How did I forget that? There was a breach recently for Docker Hub, and so there have been a number of different articles talking about how to make sure that you renew your tokens and like what the breach was about and like what the exposure was. I think, to be honest, that Docker did a pretty decent job of addressing that particular breach. I mean, they were on top of it quickly. They provided clear instructions about what happened and what they were doing around it. I thought that was pretty great. And this week here in San Francisco was Docker Hub or DockerCon. So like, obviously that could have gotten a lot. I feel like the press could have gone either way there, and it was really good to see how quickly they responded and how quickly the press of that kind of calmed down because, you know, people felt like it was being taken care of. And so I thought that was really great. But yeah, if you're using automatic builds inside of Docker, or even if you're not, you know, if you have tokens or anything else like that, like synced to your GitHub repositories, you probably received an email saying, we've revoked those tokens. Feel free to generate new passwords and generate new tokens, all that stuff. So, and then this one, let's see what the article is about. Actually, I just realized I was clicking on the camera screen. So this is Docker Hub maintenance, talking about how we will update the following. Oh, interesting. So this will be down for less than 8 hours. Docker Hub will be read only for less than 8 hours. Docker Hub automated builds will be offline for 2 hours. And Docker Hub downtime will be 15 minutes for. This is what their expectation is. This is actually a pretty good write-up. Again, yeah, doing a decent job of like communicating with their customers. So tomorrow, May 4th, from 9 a.m. to 7:15 p.m., they're expecting 2 hours of offline for automated builds. They're expecting a little less than 8 hours for read-only, which means you could still do pulls and stuff, but you won't be able to push. They're expecting downtime of 15 minutes, so just be aware. Docker's not broken. There's actually an announcement for it, so that's good. Let's see what else we got. And then down here below, we have links to the other CNI episodes. And then down below that, I have the links to the stuff that I built. So let's talk about this stuff. Before I go too far, I want to remind you about this project. And we're going to talk about the project and like some of its strengths and weaknesses here real quick, and just kind of give you a quick overview of what Kind is. So, Kind is a project that enables you, leveraging Docker and Docker, to create Kubernetes clusters. And the way that it does this, if you think about it, if it's easier to think about it this way, is that it creates a Docker instance for each node in your Kubernetes cluster. And then it leverages kubeadm to form those nodes into a Kubernetes cluster. So if I do Docker PS, if we start up our first cluster here. Here we go. All right. So go to 4. All right. Seems a reasonable size. Okay. Git. Let's start with Flannel, because Flannel was one of the earliest ones. So let's start up a cluster here. So I'm kind of skipping ahead here. I'm going to let this start, and then we'll talk a little bit more about the project. So in the to check out to pull the kind binary down, you can grab from the releases directory on the GitHub repository. So if you go to sigs.k8.io, you can grab a release directly from here. Right now they are packaging the assets that they're packaging are kind for Darwin, Linux, and Windows. And so you can grab any of those binaries and just pull them down locally and make use of this. The prerequisites, of course, are that you do have Docker installed, and that, and then depending on what you actually want to achieve for with kind, there might be other prerequisites as well. Once you have the binary, if you wanted to, you can actually also build the thing from scratch. So if you go to the docs, they also talk about, like, instead of actually grabbing the binary, you can, as long as you have Go and Docker installed, you can do go get -u sigs.k8.io/kind and then kind create cluster. When you use kind create cluster straight up, what it'll do is actually use a Docker image for all of those nodes that is hosted in Docker Hub. It'll pull that down locally and just use those images. But what if you wanted to actually use kind to build your own package? Like you wanted to add Vim to the underlying base image, or you wanted to use the binaries that, you wanted to use your own version of kubeadm, something that would actually like color log output or something. Well, kind also gives you the ability to do exactly that. You can leveraging kind, you can build specific base images, and you can build specific node images that contain all of the stuff that you want to be present on those nodes, which is actually pretty cool. But in principle, you can also build a very simple Kubernetes cluster or a very complex one. So let's talk a little bit more about what I mean by that. So I'm going to look at the configuration here that I've built. And this configuration, you can see this is still alpha. It's not a beta API yet. It's progressing in that direction. But I'm actually exploring a little bit more of the configuration options of kind in this model. For example, I'm creating a single control plane node, and then I've passed extra mounts to that control plane node to overwrite the CNI that is going to be shipped with that image. Now, I could just package my new CNI manifest into the base node, but in my case, I wanted to actually just deploy it. I wanted to overwrite that one with the flannel configuration and kind of show how that mechanism works, because it's actually pretty neat. And we're going to play with this idea quite a bit in this episode. Down below here, I have some kubeadm config patches, and this is leveraging kind of the customized model or the JSON model, in which I describe what configuration changes I need. And for customized to work generally, I need enough to anchor it so that when it wants to apply the changes that I need to create, it has some way of doing that. And so when defining these config patches, it's important that you have API version, kind, and then some identifying characteristic, like which one of these things it is. By default, kind leverages the name config as that identifying characteristic. And then down below, I can use these things to patch the objects that might be defined. By default in kubeadm, the pod subnet is actually not configured. And in my case, I wanted to actually configure it with 192.168.0.0.16. So this patch will basically just ensure that that pod cider is used for this cluster. And we're going to, again, play with this across the other things as well. So now that kind is up, if I do kubectl get nodes -o wide, I can see that I have 4 nodes. I can have my control plane node, and I have 3 workers, kind worker 1, worker 2, and worker 3. And these each have an IP address that is part of the Docker bridge. So if I do docker ps, I can see these containers. Kindest node is the image that they're based on, and this is what I mean by if you leverage kind to create a node image, this node is the one that this image is what you'd be replacing. But we're just using the one that is actually default right now. We haven't done any customization here. So each of these containers that is running in my underlying host is actually represented by one of the nodes in my Kubernetes cluster. And if I jump into the control plane node, docker exec ti kind control plane bash, Inside of the configuration of the node, this is actually where we're specifying all of the configuration that makes this this particular thing an instance of a kind node. So this is the control plane manifest. This is where kubeadm is configured. And if we look at the resulting kubeadm.conf on disk, we can see that the pod CIDR has been configured according to that patch that we described earlier. And so that's actually pretty cool. And if we go into the manifests and we look at the default CNI, we can see that this is the flannel configuration. By default, kind brings up a weave configuration. And so I overwrote that with flannel. And if I do kubectl get pods all namespaces, I can see that I'm actually running kubeflannel for all of the things. So now let's dig in a little bit more to kind of the basic network troubleshooting stuff that I think is interesting and is useful across different CNIs. Does each node get a pod CIDR? Yes, and we're going to talk about like how that works and what to look for and that kind of stuff as well. So flannel, being a really early CNI, is configured in such a way that, and actually most CNIs still do this, that they rely on the idea that the controller manager is going to allocate to the nodes a particular pod CIDR. So if I do kubectl get node -oyaml grep pod CIDR. I can see that each of these nodes, actually, you know what, let me do this a different way. So pod CIDR is part of spec. So kubectl get node dash custom columns equals name metadata name CIDR equals dot status dot pod CIDR. Nope. Is it spec? It is spec, okay. So here in this case, I can see, like just from the basic troubleshooting perspective, that each of these nodes has its own subnet. Kind control plane has 192.168.0.0.24, kind worker has 10, kind worker 2, 20, kind worker 3. That's actually pretty convenient. Worker has 192.168.3.0. This is happening because of the way that kubeadm brought up the cluster. So when I specified that pod CIDR that was the available IP space for all of the nodes, I also configured the controller manager to dole out some of those IP subnets to each node. And let's take a look at how that worked. So if I jump into my control plane node again, and we have a look at our control plane configuration, let's see, Kubernetes manifests kube controller manager. If we look at the arguments inside of here, I can see this cluster CIDR flag, which is pinned to that same global pod CIDR that we've configured, right? So 192.168.0.0/16. But then I also have a couple other arguments that have been configured. I have a node CIDR mask set to 24, and I have allocate node CIDRs true. So this is the controller manager being configured in such a way that it will take that pod CIDR, the 192.168.0.0/16, and allocate 1/24 for each node in the pod spec object. And that's actually why when I do the command here, we can see that that actually happened. As part of the registration of that node, the controller manager is going to look and see if a new node has been allocated a pod CIDR, and if it hasn't, it will allocate one for that and specify in the spec for that node what the pod CIDR will be. Now that just gets us to the point where the node has a pod CIDR. It's basically just an annotation on that. I mean, it's just an allocation of pod IPs to that node. Now we have to get down to the point where something is going to consume that and make use of it. Let's jump back into our control plane node and understand how that works. Now we're going to start talking about the CNI, the kind of the base CNI implementation, which is Container Networking Interface. That's what CNI stands for. And for that, I want to take you over to this website, Container Networking. And I think we've done a kind of a generic talk on CNI as well in a previous TGIK, but I think it's definitely worth revisiting every once in a while for the documentation, understanding what's actually happening with it and what it achieves. Because one of the things I just recently realized is that there are actually a number of different networking plugins, or there are a bunch of different networking CNI models like Calico and Flannel that rely on plugins that are part of just the generic CNI option. And in fact, most of the time, if you were to create a host port service or a host port allocation for a particular pod, that host port will be satisfied by port map. And we're going to get into that here in a little while as we describe as we talk about cilium. But I think that struck me as pretty interesting. And so these are so my point is that there are definitely a number of plugins that are used by different things. Now, let's talk about how this particular node is configured, and then we'll kind of talk about like how that all works. So let's take a look at the 10 flannel conf list. Now, this configuration is how CNI, the software built into the kubelet, is actually going to configure CNI for your pods. So when your pod comes up and it interacts with CNI to get an IP address, the very first thing it's going to try is going to try Flannel and say, hey, I need an IP address. And Flannel is going to delegate things like hairpin mode and is default gateway and all that stuff into its configuration for Flannel. But then look at this, they're chained, right? There are two plugins in line here. There's a plugin for Flannel and there's a plugin for port map. Now, what that's telling us is that it's saying that if the capability of port map is not satisfied by Flannel, then chain this other plugin, the port map plugin, and let that plugin take that action. So let's take a look at what that means. So like if I go into opt bin CNI or opt CNI bin, here is the port map plugin. So this port map plugin is actually going to be the thing that creates host port configurations for any pod that requires it. And so I think to kind of really highlight what I'm talking about here, let's actually just create something with host port, and then we'll kind of talk through like the troubleshooting part of that, which I think will highlight what we're talking about. And then we'll start talking about routing and how all of that works. So we're still kind of geeking out about CNI. Let's go ahead and grab this stuff. Let's see. Cilium. Okay, so I'm going to create a couple of manifests. I'm going to create a couple of pods in such a way that they'll be scheduled onto a node already, and then we'll kind of play with what that means. So first, let's take a look at one of these pods, echo kind worker.yaml. So in this configuration, first let me highlight, this is actually kind of an interesting configuration for a pod, and I think it's important to kind of understand what happens. So in this manifest, what's actually happening is that I'm creating just a static, just creating a normal pod. I've named it Echo, it's listening on port 80, and I've configured host port on port 80. But the interesting thing about this manifest is actually down here, where I say node name kind worker. The reason this is interesting is because that if you think about the way Kubernetes works, I could actually turn off the controller manager and the scheduler and still be able to deploy this pod. Because in essence, I've already satisfied everything that the controller manager would have to do, and I've already satisfied everything that the scheduler would have to do. So when those two things are watching for new deployments, for example, there's no deployment here. This is a pod. It's looking for pods that aren't scheduled to nodes. There's no match in this case because this pod has already been scheduled to a node. And so fundamentally, I could turn off controller manager and scheduler and still be able to deploy this pod. Interesting stuff. So let's go ahead and apply these things. I'll give these guys a second to come up, and they're up. Okay. Now, let's jump into worker one here. Now, port map is actually handling this stuff, and if you look into the documentation for the port map plugin, it's actually going to configure IP tables to route in traffic for this particular port 80, on into my particular application. So if I do ss-ln grep 80, I'll see port 80 is listening on 0. And if I do IP tables save, grep -I host port, I can see this CNI host port mechanism up here at the top and the configuration for my particular port 80, sending that traffic to the CNI set mark. And so in this case, what's actually happened here is if I do my curl against localhost on port 80, I'll be able to see my echo server. But what's interesting about this is that it's not Flannel that's configuring this. This is being configured by the port map plugin inside of CNI. And so if you're troubleshooting stuff and you realize, you know what, port map's not working the way I expect, this is a pretty interesting way to kind of troubleshoot and understand what's happening there, right? You might want to start by jumping into the CNI directory on a node and trying to understand what's actually, how those things are configured. So in our case, we're looking at this configuration. We know that we're using Flannel, which is great, and we also know that we're using port map to handle host port. But what if there was no port map configuration here? Would Flannel still be able to handle host port? That's an interesting case. We're going to talk a little bit more about that when we get to the cilium conversation. All right. So next thing I want to show you is a way of thinking about the way networking works in Kubernetes in general. Now, most models actually follow something very similar to this. Each Kubernetes node is its own entity and responsible for IP addresses on that particular node. Right? So if I do IP adder, I can see that, well, let's just do IP route. Yeah, let's start with IP route, and then we'll go from there. Okay, so most configurations of a CNI leverage some model like this. We refer to Flannel and Calico and Cilium and Canal and those sorts of things as a configuration in which that we refer to generally as an overlay network. And having been an early employee at Nicira, I can tell you legitimately, this is not an overlay network. This is an encapsulation trick. And so I want to talk a little bit more about what that means, right? What we're doing with Flannel and Calico and Cilium in almost every case, and even Canal, in all of those cases what we're doing is we're basically building a mechanism by which we can encapsulate traffic between nodes. And then we're going to install in the underlying routing table a way to ensure that we send the traffic for some destination node over the network in an encapsulated way. And so in our configuration here, you can see that we have a route for every one of those CIDRs that we talked about before, right? So if I go back here and I look at the output of that command, the There we go. If I look at these, I know that I have a CIDR that is actually going to be completely owned by each of these nodes. And if I jump into my node again and I do IP route, I can see that each of those CIDRs is being routed to some destination. Now in Calico's case, or sorry, in Flannel's case, I'm sending this traffic to, I'm device routing this traffic toward Flannel 1 interface. And that's because Flannel needs some mechanism by which to ensure that it can figure out the next hop. And so if I do bridge FDB show, I can see what's actually happening here. R-N. Oh, what? No. Well, anyway. I can see that in the FDB show, I have a configuration here where Flannel 1 has different MAC addresses. So if I'm sending traffic off to, it's not really describing what I want it to describe. Yeah, so we're leveraging Flannel to route this traffic back and forth. There's a pretty good document on understanding Flannel networking. That was put up by Anika Reddy. I'm actually going to copy this into my notes here so I don't forget to do it later. And in this document, like, he actually really gets down to the detail of how Flannel works and why it works the way it does. All right, and so as we can see already, we're routing this traffic in this way, and then brctl show. On link. Yeah. Suffice to say, this traffic is being routed back and forth between all of the nodes in Flannel. We're using VXLAN as this interface, and so there is a configuration inside of the bridge that enables us to understand where the target for show what the target for the destination is, right? So here's the MAC address for this destination, and then what it doesn't allow me to map right now is the ability for you to understand where C90 where that destination is. So Calico's, I mean, Flannel's a little tricky to understand because it has to actually route that stuff. But one thing that is interesting about Flannel that I do want to point out is like how we can actually troubleshoot the networking piece. So like I said, it's an overlay network. We're using VXLAN for the encapsulation. How do we understand that things are working? So if I do IP route, can I ping the first IP address on all of the other nodes? 192.168.1.1. Oh, really? Apt update. Apt install ping. So I can ping that one and 2.1, 3.1, 0.1. And so just that command right there is able to show me that I have IP connectivity to each host. And that's true because if I do IP adder and I look at the Flannel 1 interface, I can see that I'm actually, or the CNI interface, I can see the CNI interface has 192.168.1.1, and this is going to be true for every one of the Flannel instances, right? So every one of my nodes is going to have a CNI 0 interface, and each one of them is going to have the first IP. And so if I can ping between those things, I know that this is going to work. I know that I have good connectivity between all of the nodes. Now, moving on up the stack, how would I troubleshoot access, from a pod down, across to another pod? Kubectl get pods, kubectl exec TI kind worker bash. Okay. So let's get back into this directory and move into NetShoot. Kubectl apply-f NetShoot. So let's take a look at what NetShoot is. NetShoot is a tool that was put out by a gentleman named Nikolaka on GitHub. And what this does is it allows me to create an image that actually has a bunch of tools that already deployed into it. So let's take a look at what that image is, because you shouldn't deploy stuff you don't understand, because you never know what's going to be in there. So let's take a look at NetShoot. So this is the source for NetShoot. I'm going to link this one here as well. So NetShoot is it's basically a tool that it's a container that has a bunch of the necessary information, tooling to be able to help kind of understand and troubleshoot networking capability within the cluster, which I thought was actually pretty interesting. And there's a bunch of really interesting tooling that's already built in. So we have Apache 2 utils, we have Bird if we want to take a look at BGP configurations. We have TCP dump, curl, DHCP. We have a bunch of other tools in here to kind of help us debug and troubleshoot. The reason I'm spinning this up is because I want to be able to make use of ping. So if I do kubectl get pause again, and then kubectl exec TI NetShoot J. So with NetShoot, the way the deployment works, before I go too much farther again here, I can see that the deployment is actually configured to use host network. And that's because I wanted to actually expose to the underlying host network this set of tooling so I could troubleshoot with that tooling. So if I do IP route, I can see the same routing that I saw before. I can do, I can use ping, I can use TCP dump, I can kind of use any number of tools to actually understand what's happening here. But let's spin up a container that is not part of the host network and look at what the configuration looks like from that perspective. So kubectl run debug image equals quay, actually busybox command sleep. Guess that would have been too easy, huh? Kubectl delete debug. So we're just going to reuse our NetShoot container and put it in there that way. So this is going to be called NetShoot Nicola replicas 3. So let's jump into our container here and see what we get. So if we jump into overlay 8 bash oh, it didn't actually start, did it? What am I missing here? Oh, yeah, that's unfortunate. 1 second. Okay, so what happened there was that when I used the command from the run, it didn't parse the command correctly and put the wrong thing up, which is pretty reasonable. So let's jump into this guy, overlay, mx, bash, and if I do IP adder inside of here, I can see that I have 192.168.2.4/24. And if I do IP route from inside of the overlay pod, I can see that my gateway is 192.168.1. Wow. I can see that my gateway is 192.168.2.1. That's interesting, though. We have to figure out what that's about. But we don't have to figure out about it. We don't have to figure it out right at the moment. Although it is interesting. Okay, so my IP address is 192.168.2.4, and my default route is 2.1. So if I ping 192.168.2.1, I can see, according to my ARP, that I have the MAC address of 8A8A2 or 62D6. And so this is just straight up networking. This is the pod reaching the gateway via its own network, and I'm able to reach it and everything. And one thing that's interesting to describe here is that if I look at this IP address for this overlay pod, I can see that it's got a network size of /24. Now, if you get into like TCP a little bit, or you get into like understanding IP and TCP, what that means is that there's a broadcast domain that's been defined here, right? So this means that if there were other pods inside of this node, I'd be able to discover them just using L2 without any routing whatsoever, which is really interesting. And if you think about it, kind of represents a security problem, which is kind of part of why things like Calico and Cilium and other CNIs have come along, is to kind of improve this model. But what I'm pointing out here is that because these two, because I can see the MAC address of this other thing, so let me say ping 192.168.2. What's it? 3. 2. Okay. So what I'm pointing out here, so the other pod that's up here, if I do kubectl get pods -o wide. So 192.168.2.2 is my echo server that's sitting on that host, right? And if I jump back into that container, I can ping 192.168.2.2. And if I do arp an, I can see the MAC address of 192.168.2.2. And so if I were to actually look at what's happening on the underlying network, even if I didn't have 192.168.1.1 or router turned on, all of this stuff is able to actually communicate with each other because they're all part of the same broadcast domain. Which means that when those packets are moving back and forth between those two pods, they're never traversing a layer 3 boundary, and so I don't really have a lot of control over what's happening there. Now, 10.244.0.0 is an artifact of the fact that Flannel assumes that network, and I didn't configure it outside of that. So it's a misconfiguration, but it doesn't break us because Flannel's actually pretty smart that way. So my point is that even if we didn't have a gateway, we could actually route this traffic back and forth between these pods. And if you think about it, that means that it's because they're L2 adjacent. They're all in the same network. And then our next example, which will be the cilium piece, we're going to talk about how this is very different than the way that Calico or Canal or Flannel work. All right, so that's what I wanted to show you, that stuff. So this is basically pod-to-pod networking. So now I'm going to destroy this cluster. I think we've talked enough about Flannel, and now I'm going to show off Canal next. So we'll do kind delete cluster. And let's jump into Canal. So Canal and Calico are very different, or are very different implementations, and we'll kind of talk about how to configure how they are configured differently. So I'm doing this part, ln minus sfn, current working directory, CNI, with temp CNI. I'm doing that because in my config, I have to actually specify where the file is located. And it's easier for me to type temp CNI canal than it is for me to figure out what the right path is wherever you've deployed Git. So in this configuration, you can see I have pod sliders set to 210.244.00 instead of 192.168.00. So let's see what happens here. We'll also talk about what canal is. So kind create cluster config. Oh, my bad. All right. So this will bring up a canal cluster. So we've talked a little bit about flannel. And now we're going to talk a little bit about calico. And then we're going to talk about how calico and flannel work together to make canal, which I think is pretty interesting. The docs for canal are here. So this is a documentation for calico and documentation for canal. But one thing I wanted to point out is, like, in any case, if you're going to start troubleshooting networking, whatever the CNI is that you're using, and you should usually tell what that is by looking at kubectl get pods. And for the kube system namespace, you'll see some pod running that kind of tells you what your CNI is. It's pretty important to kind of understand, like, which one that is, and then go hit the documentation for that. I can't beat up on that enough. It's super, super important. So we're at the point where we're starting up our worker nodes. And then we'll talk about this good stuff. Okay, so get pods all namespaces. We're going to let these things kind of start up here for a sec. Now, interesting thing that's happening here. You can see that in canal, we have a ready state for canal for each pod that is 2 containers, right? So we have 0 of 2. And let's dig in a little bit more about what's happening there and what that means. Watching our control plane kind of come up and stabilize here. We have a couple of canal pods up. So let's look at that one. kubectl describe pod -n kube system canal. So there's 2 running containers here. First, there is an init container. It's not one of the 2 running containers. We have an init container wherein we're specifying the CNI configuration. And we're running this install CNI script, and we'll take a look at what actually happened there. But the CNI conf that it's applying is 10 canal conf list, and we're going to go look at what that is. And then it's also going to mount in op CNI bin, which is interesting, read only, read write, and that means presumably that it's actually going to make sure that it has the matching version of port map and other stuff configured there. But which are the 2 running containers? We have calico node running, and we also have flannel running. Kube flannel and calico node. So canal is a combination of the 2 things together, which is really interesting. Okay. Let's dig into what that means in practicality. So kubectl get nodes. We have the same kind of configuration that we had before. As far as the node and the configuration, the host names are all the same. So I'm going to move into NetShoot. We'll do apply -f NetShoot deploy. We'll go into our host port configuration, kubectl apply -f dot, kubectl get pods, all namespace, well, get pods, really, that's all we really care about. So we're bringing up that same configuration that we had in the final cluster. We're going to have our echo kind, we're going to have our echo servers, and we're going to have our NetShoot servers. Echo servers are mostly up, NetShoot is coming up. All right, there we go. So everything's up and working. Let's jump into one of the workers and see what that configuration that we talked about earlier was. So I'm going to start by troubleshooting by digging into like what the configuration of CNI is specifically. So let's jump in. So let's do docker exec ti kind worker bash etc CNI netd. So now we have two things inside of this configuration. We have 10 canal conf list, and in this case we have 3 things that are chained, which is really interesting, right? We have actually we have 2 things. We have policy being chained in, we have the plugin for Calico, and then we also have port map. So our Calico configuration, by default, this is actually how Calico is actually going to get its configuration from the CNI. So we're saying log label is info. We're going to use KDD. The data store for Calico is KDD. We're going to kind of talk about what that means here in a second. The node name for this particular one is kind worker. The IPAM configuration is host local, and we're going to use the use pod slider, which in this case is means use that pod IP allocation that the node got as part of its configuration. So this is Calico doing all this stuff. Now what's interesting about this is not all of it applies, but we'll dig into it a little bit more about what I mean by that. So then at a policy type we have K8s, and then we have this Kubernetes kube config that is actually allowing Calico to authenticate with Kubernetes to make use of that data store that we talked about. And then down below we have port map. So let's take a look at opt CNI bin. And here we have Calico IPAM, we have Calico, we have Flannel, port map, all those things are happening locally. Now, because we're running Flannel and Canal, here's the interesting thing about this layout. This is kind of nuts. So Canal means that we're going to use Flannel for routing, and we're going to use Calico for networking inside of the node, and we're going to use Calico for network policy. What does all that mean? If I do IP route, I can see the same thing that I saw before, right? I have a Flannel 1 interface. I'm routing that traffic very similarly to the way I did before, only this time I'm using 10.244.0.0 instead of 192.168. But what's on the actual interfaces that are associated with the pods, I'm getting a different thing. I'm seeing this Cali thing, and I'm doing device routing for those interface IPs up to the Cali devices. So in my underlying host, I'm actually routing 10.244.2.2 up to this device, which is our host side of a VETH interface. If I do docker ps from within this host, I can see I have echo server and NetShoot running. Oh, you know what I didn't do is I didn't create that overlay one. Let's go ahead and start that up. Kubectl run overlay. Okay, so that worked out better. So let's jump back into our host again. So I do Docker PS. I can see that I have this NetShoot, then I have that overlay pod that I created. I want to jump into that overlay pod real quick and take a look around and see how that's different than the Flannel one. So I do kubectl exec ti overlay q bash. I do IP route. Now this is interesting. This looks very different than it did in Flannel. And if I do IP adder, again, very different. So those of you who have dealt with the Linux routing mechanism understand there's something really funky happening here, and it's really worth talking about. So what's happened in this case is that we've given this particular pod an IP address with a /32 subnet. And that means that there is no broadcast domain. I'm not adjacent to anything. There's nothing else effectively within my network. And so for me to get to anything else on the network, I would have to ARP out to something. And the question is, how does that happen with Calico? The way that happens with Calico is through that IP route mechanism. If I do IP route, I can see that I do have a default gateway or a default next hop, which is 169.254.1.1, and it sends that traffic out the ETH0 interface. But what happens? Like, how is that actually all working? Can I ping other pods on the same node if I ping 10.244.1.2? Oh, and I spell it and I do it right. I could ping it. I could probably curl it. Let's try that. 244.1.2. 8080. Right, so it's working. I can actually hit it and resolve it and stuff. But if I do my arp-an command, I don't see any MAC address associated with that. So how is that working? It's not L2 adjacent to anything. If we jump back into our container again, and we look at the this Kali interface, or the way this is all working, the way that Calico does its thing is subtly different. And this is actually just in the way that the interfaces are being created, right? So if I do sysctl-a grep proxy arp. So I can see that for these Kali interfaces, proxy arp is enabled. And what that means is that from the pod, even though there's no network associated, the proxy arp, having proxy arp enabled on our side of the VETH means that when traffic tries to egress that pod, it's going to land on our underlying host. And the internal VETH, this one located in the host namespace, is going to ARP for everything. So if you want to know where the gateway is, it'll tell you where it is. If you want to know where what the MAC address of the next guy over is, or like route to the next hop, it's going to figure that out from that particular lower layer, the low-lying configuration. And so even though I can't use broadcast, there's no broadcast domain here, I can still ping all of the things inside of I can still ping all of the things within the same scope. But what's interesting is that there's no broadcast domain, so I have to route everything. That means that for Calico, things are routed all the way down to the pod. Super fascinating. And if I do my netset-rn, or my IP route, I should say, I can see the configuration is just a little, again, because we're using canal, the way that I get traffic back and forth between nodes is using Flannel. And so one of the key differentiators between this and Calico straight up is that Calico uses BGP to determine what the next hop is. In this case, we're not leveraging BGP at all. We're using Flannel because we're using canal. And that means that Flannel is going to go about doing what it already does, which is basically interact with the cluster to determine what the next hop is based on that status object for every host. So if we run that command that we ran earlier, see pod cider. So Flannel is actually being configured is being configured here, and it's going going to use that CIDR that we saw again to kind of route this traffic back and forth, and that's how that mechanism is going to work. So canal, I think, is actually really interesting because if you think about like canal versus calico, the interesting thing about the way calico and the way they differentiate is that when you're using straight calico, you're going to be making use of BGP, even if it's just a full mesh mechanism back and forth between all of the components within your cluster. Whereas with canal, you're using flannel for that routing mechanism, which means no BGP. But you are still getting kind of the enhanced experience of being able to use a /32 for a pod IP for each host. Interesting stuff. So troubleshooting is basically the same as it was before. If I jump into my NetShoot commit container, kubectl exec -ti NetShoot. I can ping, if I do IP adder, like I said before, I can see that I have 10.244.2.1 is not a thing. 10.242.0. So I have the 2.0 IP address configured, and I can ping the other .0 addresses. And so because this IP address is exposed on my host, and I can reach back and forth between all the things, this is my way of actually validating the encapsulation is working, right? If I can ping the IP addresses that are available on the other nodes, then I know the encapsulation is working correctly, and that's awesome. If it was not working correctly, then this would fail. I can ping the IP addresses on the other nodes, 244.1.2 and 3. And so I can prove that I have pod-to-pod communication, and I can prove that I have pod-to-host communication, and I can prove that I have host-to-host communication. All of those things actually allow me to troubleshoot my networks. And so that's kind of the important part of troubleshooting your network in an overlay scenario, is that you have to kind of think about it in all three layers. Like, do you have pod-to-pod working? Great. Do you have pod-to-host and host-to-pod working? Great. Do you have host-to-host working? Kind of work your way up that stack. All right. Rory has put in a... Wait, what do you mean I broke YouTube? Oh, I'm looking at the wrong chat. Okay. All right, cool. So, yeah. So that is Calico and CNI and Canal. So let's do one on cilium and kind of look at that real quick, because I think cilium is actually probably the most interesting of the bunch, and it also highlights kind of what we were talking about before. So let's get into that part of it real quick. So I'm going to do kind delete cluster, and then I'll show you my crazy cilium test, because this is actually something that came up with a customer earlier this week, and actually earlier a couple weeks ago as well. And it shows off this CNI mechanism that we were talking about before. So I want to show you this. So I'll do kind create cluster unlink temp CNI SSFN PWD CNI. Now this one's going to be cool. I think you're going to dig this one, because in this case I've actually brought up a cluster that is broken in a kind of an interesting way. And I want to show you how and why it's broken. So this actually started for me when a customer had created this host port deployment, and the host ports weren't working, and he wanted to understand why and how to fix it. And in this case, he was actually deploying cilium as a CNI. And to be fair, cilium has since fixed this problem. Like, they've actually managed to merge in the ability to provide you a mechanism to configure CNI chaining for cilium. And I have that documented here. So this is the pull request that fixes this. You can see it's merged. But it did actually highlight a really interesting break for cilium that I wanted to kind of to show and kind of explain through real quick. So even though this has been fixed on the cilium side, I just wanted to talk through it. So clear kubectl get pods all namespaces. Whoops. Kind. Delete cluster. It brought up a weavenet. Not what I wanted. Cat config. Temp CNI. Cat temp CNI. Cilium YAML. Okay, so why did that happen? Kind. Create. Cluster. Config. Something spotty happened there. I'm not sure what it was, but basically we brought up the kind of the default configuration of Weave, and I wanted to bring up the configuration of Cilium. So give me just a minute to kind of get that back online, and we'll take a look. Yeah, I think that's probably it. I probably forgot to actually give it the config. That was my bad. All right. Hello from Tunisia. Christian Waves. We have 10.254.16 is the pod slider in Flannel. In every case so far, all of my clusters I've been using 1096 as a service slider. Alrighty. Now this one's gonna be a fun one, I think. I think you folks will dig this one. Okay, cool. Okay. Git kind CNI host port kubectl create -f dot kubectl. Bunch of stuff starting up here. Yeah, there we go. So we got our Cilium configuration starting up. Let's do a watch. One of the things I do want to highlight is that I've torn down and created clusters a number of times in this episode. So shout out to Kind, because it is incredible. And if what you're trying to do is like dig into the nuts and bolts of how these pieces and parts may or may not work, it is invaluable to have kind of like the local development for this sort of stuff. If you think about it, there's like an analog for the way that your developers might try and make use of Kubernetes, right? And so, yeah. And this is Pat McGrath asks an interesting question. He says, any idea why opt CNI bin includes a flannel binary? It is historic, in fact, yeah, because effectively, since CoreOS did create CNI, and flannel was actually the default CNI for a long time, it's still there by default. But so it is definitely historic. The one that's there, I think, is actually probably not the most recent. So if you're going to deploy flannel for a configuration, you definitely want to grab the most recent. So interesting stuff. So waiting for things to come up here. Almost there, it looks like. So yeah, I mean, in this case, a little bit of history of like what I was doing this week. So I was working this cilium deployment configuration, and the customer's like, I can't get host port to work, and I said, well, here's what I'm going to do. I'm going to use Kind to stand up a cluster with cilium configured, and we'll walk through making it work for you, and then we'll talk about like why it works this way versus that way. And so I'm going to take you through that same exercise because I found it really interesting and compelling, and so we'll kind of go into that part. What's happening at the moment is we're waiting for etcd operator and a number of other things to kind of spin up, because cilium actually requires an etcd cluster to hold temporary state. Now, to be clear, if cilium is going to stand up an etcd cluster in the Kubernetes cluster as part of its pods, and then use that etcd cluster to hold state for the cluster, for identity information and things like that for cilium. When I first read that this was happening, I was like, whoa, back up the truck. Why are you doing that? Like, hosting etcd inside of Kubernetes has brought me a lot of pain over the years. And so I was really concerned that was actually a thing that they were doing. Turns out, though, that the folks at Cilium are really pretty sharp folks. What they end up doing there is they actually use it effectively as a cache. They're holding cache information for this stateful data. So if they lose that cluster, it doesn't cost them anything to recreate it, right? So if I delete that etcd cluster, the etcd cluster will be recreated by the operator, and state will be replaced inside of that etcd cluster. And they won't have lost any capability during that time or during that outage, which is actually really cool. And that calmed me right down, because at first I was like, and then after that I was like, okay, all right, I'm on board now. It makes sense. You can see that this is taking a little while to download everything, and also have a little bit more CPU load happening. So I hope it's not getting too blurry for y'all, but we're getting somewhere with all this. Another way to run Cilium would actually be for me just to leverage like a local etcd cluster that I created, but I didn't decide to do that, so I'm still kind of waiting for everything to come up. etcd. So there's our etcd starting up now. So Cilium etcd is actually beginning. So while we're waiting for that stuff to start up, I want to talk about what I mean by this is kind of interestingly broken. So if I go into Cilium and I look at the configuration of this one, I can see I'm actually getting quite a bit more creative about mounts here. So let's talk about what happens here. So in the control plane node, I'm actually populating the default CNI with the Cilium configuration so that it will be applied as part of instead of the default CNI. And I'm also populating this file called 000 Cilium port map into SCCNI netd. And the reason I'm setting this up is because I want to make sure that this is evaluated, and to evaluate it, it will actually ensure that we're chaining those two things, the port map base. And we'll look at those files here in a second once everything kind of stabilizes. Now the workers are each configured differently. In worker 1, I'm actually populating the file, and because CNI was pre-installed, all of the port map configurations and everything are already present. In worker 2, I'm actually overriding the opt CNI directory with an empty dir, because I want to make it so that there is no port map installed. So even though there may be a configuration applied, there is no port map installed. So we'll talk about how that works, what happens, what the failure case is, and how to troubleshoot it. And in worker 3, I'm just not populating the 00 cilium port map configuration. I've not actually copied that in. And so in worker 3, we're expecting the pods will start because they don't know that port map isn't working. And so once we get everything started up here, we'll talk about like how that actually manifests. So if I do get pods, I have NetShoot working. Dash in qubit system. Okay, so unfortunately for me, here's what happened. Well, I'll just fix it and then I'll tell you why. Bin opt CNI bin port map temp empty bin. So what I've done here is I've actually added the port map configuration here because I want it to actually work. So I've deleted that initial etcd pod because I need it to start another one. So here's what's happening there. Okay, so what we saw in the log was actually pretty telling. And that's actually what I wanted to talk about. So let's talk about that. So in my case, what happened here is that the pod that was created landed on kind worker 2. And you may remember from the config, the kind worker 2 didn't have the port map binary on disk. But it did have a configuration that said for it to farm out the management of host port to that binary. We can see in this manifest that host port is configured. It says host port 00, so it's actually going to try to configure a host port for this pod, even though there's no particularly good reason to do so. It's still going to configure it that way. And that means that when we go through the CNI logic is going to come down, it's going to hit the cilium plugin, and cilium is going to say, I'm not handling host port, and it's going to chain down to the port map plugin, and then it's going to go looking for that binary to make it so that it can actually stand up host port, and then it's going to fail. And it will provide you a really good log describing exactly what's happening, which is awesome. So the log says, I failed to create this pod because the network effectively expects host port, and the network CNI failed to set it up because it was expecting to find a plugin called port map, which doesn't exist inside of opt CNI bin. So you might want to put that in there, and then maybe that'll work out. I'll get pods dash in qubit system. So now we have our first etcd, and we can see that our first etcd is landed on kind worker 2, the next one is landing on kind worker 2. Let's get this guy the rest of the way up. So now we have at least one cilium process running completely. We now have 2 cilium processes running completely. Because now there's actually a cache for holding all of that state information. We have another cilium etcd pod in pod initializing and pod running. We have another cilium started up completely. We are creating a new, we're going to create effectively an etcd cluster of 3. So now we can see all of our cilium nodes, all our cilium pods are started, and we're getting all of this other stuff started as well. Okay, so kubectl get pods. We have all of our pods started, everything's working, and now we're going to dig into the cilium piece. But here's the piece that's interesting. So you remember the echo server? Let's curl each of these and see what we see. So if I do curl 172.17.0, well, first let's do this. Let's do kubectl get o wide get node dash o wide. So kind worker has 2, kind worker 2 has 5, and kind worker 3 has 4. Now, I'm expecting to be able to curl 172.02 and 172.17.05, but I am not expecting to curl 172.17.04. And here's why that is. If we docker exec into one of the workers that has everything configured, and we move TI, and we move into etc cni netd, we can see that there are 2 files in here, right? And they're kind of lexically ordered. We're giving 000 a kind of an important thing. So if we look at 000, that's where we're chaining cilium CNI and we're chaining port map. And if we look at the cilium configuration, which happens a little bit later, we're saying use cilium and the type will be cilium CNI. And if we go into opt bin, we can see that we have cilium CNI, and we can see that we have port map. And so this one has all the pieces necessarily to create stuff. And if I do IP table save, pipe grep host port, I can see host port's been configured and all that stuff works as we expect. If I do my curl test, curl http / 172.17.02 and 05, everything works as we expect, but 172.17.04 doesn't work. So why is that? Let's try that. 4. Connection refused. Let's docker exec into that guy and look around and figure out why that is. TI kind worker 3 bash the SE CNI netd. There's no 000 conf here, which means it's not doing anything. There's no way for it to get to port map. But what's also really interesting is that it means that there's no failure mode, except for the fact that it doesn't work. So the pod started, even though port map wasn't working and host port could not be satisfied, the pod still started. And that leads to behavior that is hard to troubleshoot or understand for some people, right? So like what that means is that like if I look at the other 2 pods, I'm getting the behavior that I expect, but if I look at this one, I'm not, right? Because the pod, even though the pod started, host port didn't work. If I docker exec back into the number 3 there, and I do my IP table save command that I was looking at before, There's no host port configured here. And there wouldn't be because it's not actually been created on that host. So the last thing I want to cover before we call it a day is what happens, how can I fix this though, right? So if I do docker cp cni 00 conf list, and I copy that into this pod, kind worker 3, etsy cni net d, and I jump back into docker 3, see etsy cni net d. So now I've populated the file, but remember that there's nothing wrong with the pod. So it doesn't think there's anything to fix. So it's never going to just start working. So if I do curl 172, what? kubectl get nodes dash o wide. If I curl 172.04, I'm still going to get connection refused. But here's the cool part. Let's go into host port and I do kubectl delete -f echo worker 2 or 3. Sorry. Now I haven't restarted the kubelet. I haven't done anything else like that. I'm just deleting the pod and recreating it. What do you think is going to happen? Do you think I'm going to have to restart the kubelet to get it to load that into disk or to load that into memory? That was my supposition. Which I thought was really fascinating. It works. So to break that down, that means that the kubelet loads its configuration from that directory on every subsequent call. That means that if I change the configuration of CNI, the next time CNI tries to exercise that code, it will reload that configuration from disk before going through its work, which is mind-blowing. Vast majority of times, a process that is running has its configuration loaded into memory and has no way or reason to go back and look at disk for its configuration. But this is the way that it works in CNI and in kubelet. It'll actually reevaluate that configuration on every subsequent call, which is kind of mind-boggling. So the other thing, and so I wanted to share that with you because I thought that was absolutely fascinating. Anyway, we've been at this for 2 hours. I hope that was helpful. I know that was a lot of information. I think it's helpful to kind of understand how all this stuff wires up. Before I take off, I want to show you a little bit. I want to kind of do an apples-to-apples comparison with cilium, which I think is actually one of the more interesting CNIs that are out there today, along with calico. If I jump into my overlay, pod 47 bash IP route. All right, looks okay. Default route via 192.168.3.1 and IP adder. Whoa, hold on. What? So the IP address is 192.168.3.140, but it has a subnet mask of 255.255.255.255, which means that there's no broadcast. So I do arp-an, if I do ping 192.168 3.1 arp-an. I'm still getting a MAC address populated here. That's interesting. And if I do my command where I show off the pod slider, oh, that's not what I wanted. So 3.1 is on kind worker 2. IP adder. So we can see that the MAC address that we learned was 8E05, and it was associated with 3.1. Do we have that defined locally on the node? We do have a 3.1. It has a different MAC address though, 6582. But we do have this MAC address that it had created, right? So like the MAC address that we saw in the output above, it's 8005. Do we have that one defined here locally? We do, 8005, which is the host side of the veth. So this is where things are going to get interesting. With cilium, we're doing a lot of really kind of edgy stuff with the way that packet routing happens, which I think is actually really powerful and really scalable, but it's also hard to kind of understand what's happening. So to give you some insight into it, with eBPF and XDP, we're effectively kind of using an event-driven sort of system in which when we see a packet egress and interface, we're going to take that event and that packet and be able to compile programs about what to do with that packet next. So in this case, when I've actually jumped into the cilium pod, when I type ping 192.168.3.1, and the fact that I even get an ARP packet back, that's happening because in BPF, there's a program that says, here's the configuration. Here's what I'm expecting. Here's what I want you to do whenever you see a packet egressing that port with that MAC address, that information. I want you to do this stuff. I want you to reply back. If they ARP for 192.168.3.1, this is the MAC address I want you to give them. If they try to ping 4.2.2.1, I want you to basically take that packet and send it out the default gateway and route it out externally, NAT it out over the host, just like we do with all of the other networks. If I want to ping 192.168, something that is known to me, right? Something that is known within the cluster. So if I do, actually, I do env. No, must have come up last. Oh well. kubectl get pos dash o wide. Say I want to ping 101 or 140. Oh, interesting. Three 101, 140. I can still see pod-to-pod communication. I can still ping the other pods. Right, so I'm still able to prove that encapsulation works back and forth between all the things. I'm still able to get pod-to-pod communication. But what's interesting is that all of this packet forwarding and manipulation is all happening in kernel space. I'm never actually traversing back down to user space. If you read about cilium, I think you'd find it really fascinating. I personally have found it pretty riveting about the way they do their thing. Anyway, that is our episode for today. Thank you all for logging on and sticking with me through that crazy amount of information. I hope that it was helpful. And, hit me up on Slack at kubernetes.slack.io or on Twitter, and let me know how that all goes. I'm starting a blog. You don't have to find me there, but this is a good way of getting a hold of me. Like any of these links here will actually give you a way to get a hold of me directly. So feel free to hit me up there. So thank you all very, very much, and have an awesome weekend.